Hello, everyone. My name is Wang. I'm a master's student under the supervision of Professor Rupal Mahmood. Today, I will introduce my thesis work, Effective Real-Time Reinforcement Learning for Vision-Based Robotic Tasks. A long-term objective of the general AI is to build intelligent agents that is capable of learning skills from the real-world interaction, which requires the perception of the environments. You may know that the vision is the most important link for humans to receive information about the environment. Researchers found that over 90% of information processed by a human brain is visual. Today, it is easy to fabricate cameras that are compatible to human eyes. So it is natural to ask, can we make an intelligent agent learn from camera images in the real world? To make the problem harder, the real world is a non-stationary environment. For example, a self-driving car needs to react to the changing road conditions, and a navigation system needs to react to unexpected obstacles. As a result, an intelligent agent who performs in the real world not only needs to learn from the images, but also needs to adapt to ever-changing or unseen environment. In this work, we define real-time learning as learning on the fly as the agent interacts with the environment. With the definition of the real-time learning, training a vision-based robotic agent to perform in the real world can be formulated as the real-time learning of vision-based tasks in the real world. Thanks to the progress of machine learning technology, reinforcement learning has been successfully applied to many fields, including robotic control tasks. However, extending conventional RL methods to real-time learning settings in the real world is a non-trivial problem due to the discrepancies between simulation and the real world. For example, the real world does not pause where the agent compute actions and perform learning updates. That means that a real-time learning system must compute an action within a short period of time and perform learning updates without interrupting the periodic execution of actions. As a step towards robust real-time learning of vision-based robotic tasks in the real world, with RL, my thesis aims to investigate the following two main hurdles. First, most real-time robotic applications performed in the real world have a resource-limited computer available locally. Vision-based deep RL is expensive due to the image processing unit. Second, most RL tasks are conventionally based on sensory words. Designing a sensory word function requires handcrafted features such as calculating the Euclidean distance. However, relying on such expensive and task-specific approach impedes the application of RL to changing environment or unseen environment. Besides, programming a sensory word function or vision-based task is generally hard due to the need for effective image encoder, which may not be available prior. So let's look at the first problem, the limited onboard computation problem. State-of-the-art RL algorithms and the image encoders are computationally intensive. However, a robot agent deployed in the real world typically uses a resource-limited tethered computer where a powerful workstation can be wirelessly connected to the robot. Using the small robot create tool as an example, it is tethered to the Delta Nano, a small computer, and wirelessly connected to a powerful workstation here. The problem in this thesis, we use the term local to refer to the computer. The local refers to the computer tethered to the server and the remote to refer to the computer wirelessly connected to the server. The problem is that it is unclear how much the performance of a learning system can be impacted due to the resource limitation on board. Moreover, computations of a learning system can be distributed between the two computers in several ways. Unfortunately, prior work does not systematically study the distribution of computations, nor suggest how to achieve an effective distribution to compensate for the performance loss due to the limited onboard computation. So the first part of my thesis investigates this problem by testing the following hypotheses. First, the performance of a resource-demanding learning system will degrade substantially on a resource-limited computer compared to its performance on a powerful workstation. And second, carefully chosen distributions of computations will substantially compensate for performance loss due to the limited computation resources, especially for resource-demanding learning systems. The work of the first part of my thesis resulted in a published paper accepted at the 2023 International Conference on Robotics and Automation, or the ACRA workshop. In this paper, we developed a two vision-based robotic tasks using a robotic arm and a mobile robot. We also proposed a real-time reinforcement learning system called the Remote Local Distributed System, or ReLoD workshop, to distribute computations between two computers. The ReLoD system and the two tasks were used to systematically study the impact of The ReLoD system and the two tasks were used to systematically study the impact of limited onboard computations and how best to distribute computations of two state-of-the-art RL algorithms to compensate for the performance loss. So let's look at our proposed task first. The first task is called the UR5 ReLoD Reacher. It is developed with a UR5 industrial robotic arm, and we attach the camera to the fingertip of the arm to enable image-based tasks. This task is the same task proposed by Yufeng and Rupam in their paper Asynchronous Reinforcement Learning for Real-Time Control of Physical Robots, accepted at ACRA last year. This task aims to move the UR5 fingertip to the target designated by the red plot on the and stay there as close as possible until the end of an episode. The action is the angular speed for each joint, and the actions are sent to the robot every 40 seconds. And the episode length is 4 seconds. The reward function here seems very complicated, so I won't go to the details, but the main intuition is the following. So this portion of the reward function encourages the movement of moving the fingertip of the arm to the target close as possible, and the second portion of the reward function is used to penalize the abrupt twisting of joints. As you may have noticed, the reward function needs a lot of human works and insights to be effective. So this is a good example of how hard to design a reward function for vision-based robotic tasks. Okay, so the second task is called the Create Reacher. It was developed with a mobile robot called Create2. It has two controllable wires here and here. This vision-based task aims to move the Create2 to the target designated by the paper attached to the wall as soon as possible. The action is the speed for the two wires. actions are sent to the robot every 45 milliseconds. Unlike UR5 reload reacher, create reacher will terminate the current episode as soon as possible if the target is reached. The maximum allowable exploration time is 30 seconds. If create2 does not reach the target within the time limit, the reset routine will bring the create2 to a random location in the arena. This task uses a significantly simpler reward function, which is just a -1 for each step to encourage shorter episodes. So now let's look at our proposed ReLoD system. The ReLoD system parallelizes and distributes computationally expensive components of RL systems between a local computer and a remote computer to reduce the overhead of real-time learning. In my thesis, I used the ReLoD to distribute two state-of-the-art RL algorithms, soft actor critic and proximal policy optimization, the SAC and the PPO for short, to get a better coverage of different types of algorithms. SAC is an off-policy resource demanding algorithm since it updates the policy at every time step and it requires a large replay buffer to hold its past experience. PPO is a relatively simpler on-policy algorithm since it only updates the policy every few thousand steps, and its replay buffer needs to hold only a few episodes generated on policy. ReLoD supports three modes of operation: remote only, remote local, and local only. As the name suggests, the remote only allocates all computations on the remote computer, and the local only allocate all computations on the local computer. Details about the remote local mode will be given in the next slide. Okay, so using SAC as an example, its remote local mode consists of two main components: the local agent and the remote agent. The local agent has three processes that run in parallel on the local computer. We are an agent interface process, a local send process, and a local receive process. The agent interface process computes the actions to take in the environment. The local send process sends the interaction samples to the remote computer here. And the local receive process receives the updated policy from the remote computer. The next is the remote agent. It also has three parallel processes. They are named replay buffer process, update process, and the learner interface process. The replay buffer process samples actions for learning, and the update process updates the policy with the mini batch. The learner interface receives samples from the local computer and send the updated policy to the local computer. As you can see from the image, the most expensive components of the computation here is the update process, the replay buffer process, and the agent interface process. So as you can see from the image here, the ReLoD system distribute. As you can see from the architectural image here, the remote local mode of the ReLoD distribute the most computationally expensive components of SAC between two computers to take advantage of both. The SAC implementation we used for this work is the asynchronous SAC proposed by Yufeng and Yuan in the same ACRA paper, and the PPO implementation is spin-up PPO. We also use the same neural network architecture proposed by Yufeng and Rupam to parameterize policies for SAC and the PPO. It includes three networks: the image encoder network, the critic network, and the actor network. The image encoder network is only used for image-based tasks. The details about the asynchronous SAC and the neutral network can be found in their paper. So we first compared the performance of the local-only stack on two computers, a resource-limited computer and a powerful workstation. We use the Lenovo laptop as a resource-limited computer. It has an Intel i7 CPU, a low-end NVIDIA gaming GPU, and a 16 GB memory. We changed some hyperparameters to reduce the resource requirements of stack on the laptop. The powerful workstation is an AMD Threadripper workstation. It has an high-end NVIDIA gaming GPU and a 128 GB memory. In addition, we also want to investigate how stack would have performed on a heavily resource-limited computer like Jetson Nano. Since the Jetson Nano are commonly used for controlling some small robots. However, when ReLoD was configured to local-only stack, Jetson Nano could not run the system fully on board, as its software and hardware architectures are not optimized for updating weights, neural net weights. So Jetson Nano took about half a second to complete one update on average, and it became unresponsive after a couple of updates. To overcome this limitation and get some empirical upper bounds of its performance, we used the laptop to emulate the capability of the Jetson Nano. We reduced the update rate to 1 update per 8 steps and reduced the memory to 4 GB. So the result is shown in this figure. The x-axis is the time steps, and the y-axis here is the average episodic return. The gray curve here shows the performance of stack on the powerful workstation, referred to as the local workstation only in the figure. It attained the highest return among all tasks, all results. Next, the purple curve shows the performance of stack on the laptop, referred to as the local laptop only. In the figure, it shows the performance of stack on the resource-limited. It shows that the performance of stack on the resource-limited laptop dropped by about 28% on average compared to its performance on the workstation. Last, the green curve shows the performance of stack on the emulated Jetson Nano. This variant struggled to learn a comparable policy within the same time frame. The result confirmed our hypothesis that the performance of resource-demanding learning system like stack would degrade substantially on a resource-limited computer. Do you have any questions?
Why there is such a large performance difference when you limit?
Yeah, so I'm going to talk about later. Yeah.
Are you muted?
Pardon me?
Okay. Yes.
Okay. So next, then we investigated how to utilize the resource of a wirelessly connected workstation to compensate for the performance loss. We use the most common setting in practice where the robot is tethered to a small resource-limited computer and wirelessly connected to a powerful workstation. Stack was tested on UR5 visual reader and the create reader, where PPO was only tested on the UR5 visual reader. We used the same laptop as the local computer for UR5 visual reader. For create reader, we used the real Jetson Nano as a local computer. The remote computer for both tasks is the AMD Threadripper workstation. The orange curve shows the performance of the remote-only stack on the two tasks, referred to as the remote workstation only in this figure. Again, the x-axis is the time step, and the y-axis is the actual return. Next, the blue curve shows the shows the performance of the remote local stack on the two tasks referred to as the remote workstation, local laptop, or local Jet Nano. These two figures suggest that stack's remote local mode consistently compensates for the performance loss of stack on both tasks. The purple curve shows the performance of the local-only stack on the laptop, referred to as the local laptop only. Note that due to the hardware limitation of Jet Nano, local-only stack was not drawn for Jet Nano. By comparing this orange curve and the purple curve, we found a counterintuitive result that stack's remote-only mode hardly improved its performance over the local-only mode that runs on a resource-limited computer. This is surprising since this mode fully utilizes all resources of the remote workstation. We attribute the relatively poor performance of the remote-only mode to the latency in communicating the actions over Wi-Fi, which will not occur in the other two modes. So our result indicates that without careful consideration, using a powerful remote computer may not result in any performance improvement. Okay, Jiaming, so did I answer your question?
Yep. Is it because like latency?
Yeah. Okay, so let's compare the performance of the remote local mode to the best performance obtained by the local-only stack run on a powerful workstation. The best performance is shown as the gray curve here. As you can see, the remote local mode almost fully recovered the performance loss. The result confirms our hypothesis that carefully chosen distributions of computations would substantially compensate for performance loss, especially for resource-demanding learning systems. However, the remote local mode only benefit computationally intensive algorithms like SAC. The figure on this slide shows that PPO's performance is nearly the same across the three modes. This result is not surprising since PPO only updates policies at the end of that episode. Thus, the distribution mode shouldn't impact PPO's performance as long as the computer can perform action inference promptly. Now let's compare the performance of SAC and PPO across the three modes. The two figures indicate that SAC substantially outperformed the PPO on complex robotic tasks. All distribution modes of the SAC attended more than twice the return attained by PPO in a shorter time frame. Compare here and here. So this video demonstrates the learned policy of SAC on the creator tool. Right, so okay, first is the initial policy. You can see there is no meaningful movement. So after the training, the agent learns to reach his target. And also we also tested on some head-on task with a larger arena. And this is a learned policy. You can say try to reach the target over here. Since that this target is closer, so it tries to reach the target closer.
This is on the previously learned policy?
Yeah. Oh no, actually this is a
retraining.
Yeah, retraining, yeah. And this is a demonstration of our UFM task. You can say that this is the stack behavior. You can say it tries to move the camera to the target, and this is the camera view here. Do you have questions? Okay. Conclusion. The first part of my thesis investigated how much the performance of a learning system is impacted due to resource limitation and how to utilize a wirelessly connected powerful computer to compensate for the performance loss. For this purpose, we introduced a two vision-based task and the ReLoD system. Our experiment demonstrated that when SAC runs on a resource-limited computer, its performance could be substantially reduced. Moreover, solely deploying all computations of SAC on a wirelessly connected remote workstation may not improve the performance due to the latency. On the other hand, our results suggest that performing local action computation and remote policy update compensates substantially for SAC's performance loss. However, this distribution may not benefit all RL algorithms since PPO performance was nearly unaffected by the distribution mode. Thus, our results show that without careful consideration, solely adding a powerful computer may not result in any performance gain. So now let's look at the second problem of real-time learning, designing of reward functions for real-time vision-based tasks. In conventional RL, these rewards are used to facilitate faster learning and guide the agent to a reasonable solution. But these rewards need to be revised in the vision-based real-time learning setting. First, since this reward function depends on the environment's domain knowledge, it is difficult to design a dense reward function capable of capturing the ever-changing nature of a non-stationary environment. Second, handcrafting a dense reward function based on image is tedious, as the effective image encoder for extracting useful information from image is generally not available prior. Third, dense reward often mislead the learned policy in a suboptimal way, since the handcrafted reward function reflects the designer's preferred behaviors. Thus, in the vision-based real-time learning setting, it is beneficial to work with reward signals that is independent of domain knowledge and prior image encoders, but without misleading the solution in an undesired way. For tasks where we want to reach the goal state as soon as possible, there is a simpler alternative to dense rewards. That is, the reward can be a negative constant number, like -1 for each step. We call them minimum time tasks. Similarly, if tasks are vision-based and the goals are represented as images, we call them vision-based minimum time tasks. Using the minimum time formulation, the task designer can easily avoid the aforementioned three problems by focusing solely on recognizing task success rather than trying to get the learned policy with domain knowledge. Unfortunately, minimum time tasks are hard to solve due to the sparse successful episode. Not to mention the vision-based minimum time tasks. So as a first step toward robust learning of vision-based minimum time tasks, the second part of my thesis aims at proposing guidelines to determine if a minimum time task is solvable by SAC before actual training. Let's define what is minimum time task. First, all minimum time tasks need to have a set of terminal states. An episode is set to complete when the agent reaches the goal state. If the agent does not reach the goal state within a given time limit, we reset the agent and the environment in such a way that the objective stays the same, but the agent moves to a different location. Since resetting the agent has an associated time cost in the real world, we penalize the agent when it fails to reach the goal state within the time limit. The penalty can be the number of time steps required for resetting the agent. The reward is -1 or can be any other negative numbers. For example, consider a task where the reward is -1, the time limit is 100, and the penalty is 20. The agent timed out 3 times and finally reached the goal state within 25 steps. So then the return just add up these numbers to 385, and the length of the episode is also 385. The work of my second part of my thesis resulted in a paper submitted to the 2023 International Conference on Intelligent Robots and Systems, or ReLoD for short. In this paper, we formulated the midterm task and demonstrated that SAC could effectively solve real-time minimum time task in both simulation and in the real world. We also developed the 2 simulation tasks and the 3 real robotic tasks, the benchmark minimum time tasks. The main contribution of the second part of my thesis is to propose and test the guidelines to determine whether SAC can effectively solve a minimum time task based on the performance of the initial policy. So let's first look at our proposed simulation task. The first task is called minimum time reacher. It was derived from the DeepMind control suite. We converted to the minimum time formulation, that is, the reward function is changed to -1 for each step. The task aims to move the fingertip of the robotic arm to the target, designated by the red there on the 2D screen, on the 2D plane. Minimum time reacher has 3 subtasks: easy, hard, and extreme. So the easy, the size of the target is largest in the easy task, and the size of the target is virtually a point in the extreme target. For each subtask has 2 variables, visual and non-visual. For the non-visual task, the observation includes the joint information and the vector around the fingertip to the target. For the visual task, we removed the vector from the fingertip to the target, as this information should be inferred around images. We stack 3 consecutive to provide history to the agent in the visual task. The action is applied torque to the 2 joints. At episode terminations, we reset the agent and randomly generate a new target for the next episode. Now we show some preliminary experiment using SAC to solve minimum time tasks. The algorithm is SAC. The task is non-visual, which are easy, non-visual, which are hard, and then non-visual, which are extreme. The total environmental steps is 200K, and the time limit is 1,000. The initial policy, we initialize it to a normal distribution with 0 means and the unit covariance. So let's see the result here. So the x-axis is the time step, and the y-axis is the episodic return. As shown in this figure, SAC can effectively solve the non-visual reacher easy within 200K steps. Where there are some signs of learning shown here. In the non-visual feature hard environment, the learned policy after 200K steps is not quite successful. One possible explanation is that the initial policy can stumble upon the target more frequently in the richer easy compared to the richer hard. To test this explanation, we use the SAC to solve the richer extreme task, whose target is virtually a point on the plane. Since the richer extreme task is significantly harder than the richer hard, we suspect that no learning will happen. As expected, SAC failed to learn an effective policy on richer extreme. There were no successful episodes within the 200K steps. As a result, no meaningful learning curves could be plotted here. So at least our preliminary result confirmed that SAC can reliably solve minimum time task under some conditions. So we further define the difficulty of a minimum time task by counting the numbers of target hits with the initial policy in 20 case steps. So then we investigated what factor could impact the difficulty of a minimum time task. One evident factor is the exploration strategy. My thesis does not focus on exploration. Instead, we focus on an often ignored parameter in task specification, the time limit. Intuitively, a large time limit will increase the chance of reaching the target since it gives the agent more time to explore the environment. However, a large timeout will only hurt the exploration if the agent gets stuck in some uninformative states. Thus, the optimal time limit should be task dependent. In short, we treat the time limit as the tunable parameter to tweak. We hypothesize that the choice of time limit can directly affect the overall learning performance as a correlation exists between the frequency of reaching the goal state and the final performance. Next, we tested the hypothesis. The task we used is minimum time boring curve and richer. We have introduced the minimum time feature already, so let's introduce the minimum time boring curve here. The minimum time boring curve aims to put the small ball into the receptacle there. It is also derived from the DeepMind control suite. Minimum time boring curve also have two variants, visual and non-visual. For the non-visual task, the observation includes the position and the speed of the ball and the receptacle. And for the visual task, we remove the position information since that those information should be inferred from the images. We stack 3 consecutive images to provide history to the agent. The action is a force applied to the receptacle. The reward is -1 for each time step. We measured the difficulties of 2 tasks for a set of time limits as listed here. The x-axis is the time limits, and the y-axis is the number of target hits. It reveals that the time limit indeed affects the agent exploration. It also demonstrated that the optimal time limit is task specific. Note that the richer extreme has significantly fewer target hits compared to the other tasks. Although the difficulty was measured on non-visual tasks, this plot applies to both visual and non-visual tasks since their initial policies and the terminations are same and independent of image. So next, we tested whether the number of target hits affects the training performance. The task we used for this purpose is non-visual boring cup, visual boring cup, non-visual richer, easy, and non-visual richer hard. For each number of target hits and environments, 30 test runs were performed. The learning performance is measured by averaging all points of a learning curve for a certain number of target hits. The results are shown here. The x-axis is the number of target hits, and the y-axis is the average return along a learning curve. So the shorter the bar is, the better the performance is. It shows a clear relationship between the number of hits and the performance. So clear relationship here, except for some very short time limit. However, the short time limit should be avoided in practice since they may result in suboptimal behavior. As the time limit become larger, the correlation, the number of hits and the performance correlates well. Thus, the result confirms our hypothesis that the choice of time limit can directly affect learning performance. The direct correlation exists between the frequency of reaching the goal state and the final learning performance. So based on our observation, one strategy for time limit selection is to choose a time limit as small as possible, as long as there is sufficient number of target hits and is larger than the expected minimum steps to reach the target. We consider that achieving an average of 10 target hits per 20K steps is sufficient for successful learning. So why we choose the number 10 here? 10 good episodes in 20K steps means that the probability of sampling a true terminal state is about 1/2000. Including the terminal state in the policy update is important for learning correct value functions. So since we use a mini batch size of 256, we estimate that approximately 1 out of 10 or 8 mini batch updates would involve the terminal states. So additionally, including at least 10 terminal states in the discrete buffer will also increase the diversity of samples. So our simulation results show that this choice works well. Okay, so our guidelines are summarized here. So first, initialize the weights of the last layer of the policy network to the Gaussian distribution, collect the numbers of target hits for a set of 10 limits using the initial policy, select the time limits under which the number of target hits is larger than 10, and then select the time limit should be larger than the expected minimum steps to reach the goal state. Start from the smallest, select the time limit, and use our chosen hyperparameters to train the task with stack. So we tested our guidelines by following them on 6 head-out tasks, 2 simulation tasks, and 4 real robotic tasks. The 2 simulation tasks are the visual feature easy and the visual feature hard, and the 4 real robotic tasks are the create reacher, UFI mean time reacher, vector charger detector, and a Franca mean time reacher. The details of the new environments will be given later. For simulation tasks, we tested a timeout, and we tested 3 timeouts: 50, 100, and 500. According to the timeout versus the hits plot here, they all have enough target hits except the feature harder with the timeout, which is the time limit 500. In this case, it has less than 8 target hits. Okay, so data collection on the real robot is time consuming. Hence, we only tested 3 timeouts for 3 time limits for the Franca mean time reacher, and heuristically choose one for the other tasks. The time limits chosen for each robot are summarized in this table. So they all have enough target hits. According to our hypothesis, learning should happen for all tasks except for the reacher harder with the time limit 500. Since that the target hit is less than 10. It may show some sign of learning, but achieving stable learning may be impossible. So we utilize the ReLoD system to facilitate effective learning on all robotic tasks. So let's look at the setup of the new environment. The UFI mean time reacher is a minimum time formulation of the UFI visual reacher. We especially changed the reward function to -1 to convert it to the minimum time task. The modified task aims to move the fingertip to the target as soon as possible. If the current episode does not terminate within the time limit, the reset function will move the arm to a random poster and keep the target location unchanged. Okay, so due to the time limit, I'm gonna skip those slides. So the ideas are the same. Just move the arm to the target as soon as possible. So factor is also the same, to move the factor to its target as soon as possible. So let's look at the performance of SAC on the two head-off simulation tasks. So as expected, we observed the successful learning on all the simulation tasks except for the feature harder with a 10 out of 500, which is here. So it confirms that the usefulness of our guidelines in predicting the learning performance of minimum-time simulation tasks. So let's look at the SAC's performance on our robotic tasks. So yeah, so the successful learning curves of the 4 robotic tasks confirm the usefulness of our guidelines in predicting the learning performance of the real robotic tasks. So let's look at the learned behavior here. This is the create Richard. This is the initial policy. It's quite random and no meaningful movement can be seen here. So after some trainings, it reached the target. It comes very close to the target, almost touches it. Okay, so due to the time limit, I'm gonna move to the next one. This is the behavior of Franca meantime feature. Although this target was fixed in the training, it's got we can move it during the testing, so that the Franca feature also can check the objective. Okay, so let's move to the next one, the UFI meantime feature. This is the initial policy, so this is there is no meaningful movement. So after training, it starts to reach the target. I mean, compared to the previous version, it moves much faster. So let's move to the last one. This is the vector. It tries to save this charger. So it saves the charger and then reset. And then this is the new episode. It learns to turn around and save the target. Yeah, so save the target, reset. So conclusion, for the second issue, we focus on effectively solving minimum time tasks with a reward of -1 for each time step. Through an empirical investigation of the performance of SAC on multiple question-based minimum time tasks, we identified that an agent could achieve successful learning performance if it reaches the target often enough using its initial policy. We estimated that the time we established that the time limit should be a tunable solution parameter instead of a problem parameter in the minimum time task. We also outlined the useful guidelines that practitioners can use to determine if the minimum time formulation is suitable for their tasks. Our work is the first demonstration of using a single reinforcement learning system to achieve real-time learning of vision-based control of multiple physical robots from scratch in the minimum time formulation. Thank you. Any questions? Thank you. Oh, there are some things in the chat channel.
So Ian?
Yes.
Yeah, you can take questions from the room or also from Zoom, but remember that we have an exam sharply at 1. So
yes.
Yeah, you need some setup time for that. So let's just have 5 minutes for questions.
Sure. So 5 minutes questions. Yeah, sure.
This might not be something that makes sense, but is it possible to, in something like this, to try to dynamically change, like for example, your for your 2D feature? like to dynamically change the target size? So as it gets better to reduce the target size? And would that be helpful or would that?
Yeah, I think it's possible. Yeah, so if you make the target size larger, then definitely you are making the task easier, right? So when you are making the target smaller, it may fail to reach the target.
But
Even
if you start with an easier thing.
yeah, that
harder,
is yeah.
harder, that might.
Continue on learning.
it.
Yes, right. I tried it. Yes, I tried it. It worked. Yeah,
Oh,
yeah.
okay,
But I
cool.
didn't feel that. Yeah. Yeah. Okay. Any questions? Other questions?
You have a slide comparing stack and PTO in the Richard task, and I was wondering, one of them is off-policy learning algorithm, the other one is on-policy algorithm. And I was wondering, they run for the same time step, and what are the corresponding time that
Yeah.
is
So
spent?
yes, I agree. So the fact is off policy, so that is way more sample efficient. I think for a fair comparison, we should run PPO longer. However, I think that we are comparing its performance within a specific time period. So let's say we want to learn the task within 3 hours, which algorithm should we use? So that's why. So we keep the wartime same.
Oh, so the time step is the what time step?
Kind of, yeah, because we use the same step size. I mean the action cycle time.
I see.
So the word time should be same here. Yeah.
Okay.
Okay. Thank you very much. I have to go to my defense.
Thank you.
Thank you.